Welcome to the General Chemistry Fundamentals series presented by MCAT Genie. In this video, we're going to discuss Lewis dot structures, how to draw them, and valence electrons, and how they're important for the bonding in atoms, molecules, and ionic compounds. The valence electron count is very critical to understand the reactivity of certain elements and why they have certain chemical properties. As I've discussed in prior videos with electron configurations and the periodic trends video, the group numbers, if we skip over the transition metals, we'll ignore those for now, are aligning with the valence electrons that we can expect in each group. So group 1 has 1 valence electron, group 2 you can expect 2. Look at the second number as we move here, so 3, 4, 5, 6, 7, and 8. So as we zoom in here, we can see an example of the fluorine atom in the ground state. The 9 electrons that it does have should be organized in the 1s, 2s, and 2p orbitals. The 1s orbital will consist of the 2 inner electrons, which are in the core, as you can see in the first energy level, n equals 1, principal quantum number. And the remaining 7 electrons, which are valent, will be in the 2s and 2p orbitals, which there are 3 2p orbitals. Our 1s has 2 electrons, 2s has 2 electrons, and 2p has 5. If you're going to count the valence electrons for the majority of the elements that you'll be dealing with, you're going to have to look at the highest energy level shell, which is the second shell. Therefore, you need to add the 2 electrons that are in the 2s subshell, as well as the 5 electrons in the 2p subshell. So 2 plus 5 is 7, and therefore you can see 1, 2, 3, 4, 5, 6, 7 electrons in the valence shell. And fluorine's ultimate goal is to gain 1 more electron in that shell so it can meet the octet rule and be isoelectronic to the noble gases. In this case, it wants to be isoelectronic to neon. That last electron would be in the 2p orbital, turning this into 2p6. And at that point, we would say that fluorine turned into fluoride. Due to the addition of an electron, we're going to say that fluorine, becoming fluoride, now has a 1- charge. From this table, you can easily see the valence electrons that are relevant for every single element on the table. So if we're looking at the second period, then we need to look at the second energy level electrons. So that would include the 2 and the 2p all the way up to neon. When we get to the third period, you'll see that that includes the 3s and the 3p electrons. When we're talking about the transition metals, it can lose from the s orbital before it loses from the d orbital. So those are an exception and hard to predict. But besides the transition metals, you should be able to look at the highest energy level, principal quantum number, and make your decision on which valence electrons are the furthest away from the nucleus. Here we have a table that shows some typical atoms that you'll have to deal with on the test and their electronic configuration. Their core electrons are being represented by this bracketed neon, meaning that all of the 1s, 2s, and 2p electrons are within the core. Because all of these atoms are within the third period or the third row, then we're going to pay attention to their third energy level electrons. Therefore, sodium has 1 valence electron, magnesium has 2, aluminum will have 3, combining the 3s2 and the 3p1. Silicon will have 4, so on and so forth. And you can see that symbolized by the Lewis dot structures here. So very simply put, whatever the number of valence electrons there are, which is typically up to 8, then those are the dots that you will draw outside of the chemical symbol. So going back to the Lewis dot structure of fluorine, based off of our discussion from before, we know that fluorine should have 7 valence electrons, so I will draw 7 dots outside of fluorine. Now, this means that if another atom, such as hydrogen, comes along and wants to form a bond with fluorine, then the fact that fluorine has 7 valence electrons and hydrogen has 1 means that we can make both of those atoms happy by bonding them together. So if we rearrange the electrons outside of fluorine as such, and I put a hydrogen over here, Well, the valence shell of hydrogen has one electron, and its valence shell will be full because hydrogen only has one 1s orbital and would be full with two electrons. Therefore, this represents a single bond between hydrogen and fluorine. Another way you can draw this bond would be as a line or a dash. This is very common to depict a single bond, which involves two electrons. You can think of it as one on one side and the other on the other side of that line. Now, keeping the octet rule in mind, and we know that most valence shells are full with 8 electrons and most atoms are happy that way, we have to keep in mind that hydrogen and helium are happy with 2 electrons because their valence shell is full once the 1s orbital is full. There are still some exceptions to the octet rule besides these. So in the case of boron, which is in group 13, so out of the main group elements, it should have 3 valence electrons. Boron is stable and happy without having 8 electrons, so it is an exception. An example of a molecule where we don't meet the octet rule, but the molecule is stable, would be boron trifluoride with 3 fluorines. If you look closely, you can see that there are only 6 electrons surrounding boron, which does not meet the octet rule, but boron is okay like this, so it's a notable exception. Another exception could be the expanded octet that, for example, phosphorus, as well as sulfur, chlorine, and xenon can have. So the main thing to pay attention to is that once we are n equals 3 or higher in terms of principal quantum number or shell, then there's a possibility for an expanded octet. An example of this using phosphorus would be phosphorus pentachloride. So phosphorus being in group 15, we can expect it to have 5 valence electrons, and it's capable of bonding with 5 chlorines. So if we count the number of electrons directly being shared with phosphorus, then we'll see that there are 10 valence electrons outside of phosphorus, which is clearly greater than 8. And the reason it can have this expanded octet is because when we get to n equals 3 or greater, we gain access to d orbitals, which can contain greater than 8 electrons. And the extra electrons can be situated in the d orbital, which is known as expanded octet, and still can be stable while not maintaining the typical octet rule. For the sake of the test, I wouldn't worry about this or lose sleep over it, but what I would do is keep that in mind so that if you do see an element that is n equals 3 on the periodic table or greater, then there's a possibility that an expanded octet could occur. So for example, if we were to draw out the Lewis dot structure of carbon dioxide, we would start off by drawing carbon, which has 4 valence electrons because it's in group 14. We know that there are 2 oxygens, so on either side, we need an oxygen. So there are going to be 2 carbon-oxygen bonds, but what will these bonds look like? So let's draw out the valence electrons for oxygen, which there are 6, because it's in group 16. And so oxygen's desire is to gain 2 electrons each, and carbon's desire is to gain 4 electrons. So what we need to do is rearrange the oxygen's electrons so that way carbon can also have 8 electrons outside of it, as well as each oxygen. To do that, we would simply move 2 of the electrons from oxygen closer to carbon, and this is going to form what's known as a double bond. So since there are 4 electrons being shared between carbon and oxygen on each side, we are going to form 2 double bonds. So you can represent that using these lines. So indirectly, what I'm introducing to you is a concept known as formal charge. The proper definition for formal charge is the valence electrons subtracted by the lone pair electrons plus 1/2 of the bonding electrons. The purpose of formal charge is to help us assess whether or not we have formed the most stable molecular structure when it comes to the bonding between the different atoms and how the electrons will be shared, whether it's going to be single bond, double bond, triple bond, and in what arrangement. For the sake of the test, doing this type of calculation mathematically is not going to be necessary because I'm going to show you a little trick that you can do visually. So if we come back to the example of carbon dioxide, how do I know that this is the most stable structure? The trick that I use to find formal charge is I count the number of dots and I add the number of sticks or lines that are surrounding a given atom, and I need the dots plus the sticks to equal the valence electrons that that atom should have. So in practice, oxygen, I expect to have 6 valence electrons. So I count up the dots, 1, 2, 3, 4, and I add the sticks, 5, 6. So to me, that means that the 6 valence electrons and the 6 dots plus sticks, I know that sounds weird, but if you subtract them, you get a formal charge of 0, and 0 is the most stable. For carbon, I expect it to have 4 valence electrons. There are no lone pairs, so there are no dots on carbon. Don't expect lone pairs on carbon. It almost never has any. And so I add up the sticks and I see that there are 4 sticks. Therefore, 4 minus 4 gives me a formal charge of 0, and that is the most stable, so that's perfect. The same thing we did on the left side would also apply to the right side, and so the formal charge of that oxygen is 0 because everything has a formal charge of 0. This is absolutely the most stable configuration for carbon dioxide, and I really don't expect many other resonance forms. Since I mentioned resonance structures, let's do a quick definition of what resonance is. So resonance is when electrons can delocalize and they can distribute themselves differently within a molecule. There can be multiple resonance structures that can exist and be equally stable, and the molecule is not going to exist in any one of those resonance states, but instead is going to be a hybrid that's contributed from the different resonance structures that are possible. So it's more dynamic than it is static. Let's go into some examples of this. Let's say I ask you for the Lewis dot structure and the resonance structures of ozone. And ozone is known as O3. How should we organize the 3 oxygen molecules correctly? So let's draw each one out. And now we have to ask ourselves, given that each one has 6 valence electrons, how will the bonds form between these oxygens? And so we need to decide when there will be a single bond or if there will be a double bond in between the oxygen atoms. So if we try to organize these oxygen atoms together in the ozone molecule and we want to give each one an octet, we're capable of giving the first oxygen an octet in a single bond with the central oxygen, which also has an octet, but the third oxygen has an issue where it doesn't actually fulfill its octet because there are only 6 electrons surrounding that third oxygen. So how do we get to a point where all of these oxygens are happy and fulfill their octet? So let's say we try to solve that issue by moving some of the lone pair electrons on the central oxygen and forming a double bond between the second and the third oxygen here all the way on the right. Another way we can depict the bonding between these 3 oxygens will now be a single bond and a double bond. So if we count each of the sticks or the lines, so the single bond is considered 2 shared electrons, and a double bond is considered 4 shared electrons, each of which contains 2, then we can meet the octet rule for all 3 of these oxygen atoms. But if we go and determine the formal charge of the oxygen atoms, then we see a different story. So if you take the normal valence electron count of oxygen, it should be surrounded with 6 electrons. But when you count up the sticks and the dots, there's 1 stick and 6 dots. That means there are 7 electrons, or the number 7, surrounding oxygen, which is 1 more than it should. Therefore, a formal charge for the first oxygen is -1. If we look at the second oxygen and do the same thing, well, it's going to add up to 1, 2, 3, 4, and 5. So therefore, the formal charge here is going to be 6 minus 5, and the central oxygen has a formal charge of +1. But the third oxygen, all the way at the end, is the most happy because it has 1, 2, 3, 4, 5, 6, which is the same number. Therefore, 6 minus 6 is 0. And so therefore, that oxygen is technically the most stable in terms of formal charge. So in reality, we could flip which side has the double bond and which side has the single bond. And that would result in a very similar situation, except the negative side would be this side. The positive would still be in the middle, and this side would have a formal charge of 0. What I want you to notice is that the +1 and the -1, because 1 is plus and 1 is minus, will technically give us a formal charge combination of 0, and therefore the entire molecule has a formal charge of 0, which means that its most stable resonance structures is between the two that we just went over. But as I said, in nature, the reality is neither of these sides is going to be a real double or a single bond, statically speaking. It's actually going to consist of two single bonds, and the valence electrons are going to resonate between all three of the oxygens. So that's what's known as delocalized pi electrons. This concept of resonance will come up again, I guarantee it. And it's actually very, very important for understanding organic chemistry better and biochemistry better, as well as when we discuss the inductive effect within acids and bases, as well as other analytic techniques. I'm not going to jump too far ahead, so let's just keep it at this for the time being. I'll give you another example of resonance structures with a different molecule. So another example I can give you is the Lewis dot structure of nitrate. And what you're expected to know about nitrate is it involves one nitrogen atom, three oxygen atoms, and overall has a negative charge, which means that this is considered a polyatomic ion. So let's try and draw out nitrate, and we see that we have one nitrogen, so most likely this is going to be our central atom, and then surrounding it will be three oxygens. If you were to try the oxygens as a central atom or any other orientation of this, you'll find out pretty quickly from trial and error that none of that will work. So just so you know, if there's one atom within a polyatomic ion, usually that's the central atom, and the other atoms, which are typically oxygen, will be surrounding it. So keep in mind that because there is a negative charge on this polyatomic ion, that means it's going to have one more electron than we would expect in the ground state. So nitrogen's job here is to try to make everyone happy with the 5 valence electrons that it normally has. And since we're dealing with a polyatomic ion, as we said, we have an extra electron to work with. So why don't we donate 2 electrons to each of the oxygens? So another way we could represent this is by saying that there are 3 single bonds coming off of nitrogen. Well, the issue we run into is that nitrogen only has 6 electrons surrounding it, so it doesn't meet the octet rule, which is unacceptable. So the solution to that would be to make at least one double bond. Now nitrogen is happy in terms of the octet rule. If we look at all of the oxygens, they are also happy in terms of the octet rule. But the issue we run into is going to come back down to the formal charge. So if we look at the formal charge of nitrogen at the moment, we're going to notice that nitrogen only has 4 sticks surrounding it, but it's supposed to have 5 valence electrons. So essentially the formal charge of nitrogen is going to be 5 minus 4, which is positive 1, which indicates that nitrogen has a formal charge of plus 1. If we look at the formal charge of the oxygen with the double bond, this one is going to be the happiest because it's supposed to have 6 valence electrons and there are 6 sticks and dots surrounding it. Therefore, the formal charge is 0. You will get used to seeing that oxygen is the happiest in a double bond if it's only bound to one other atom. In the other scenarios, when you see that oxygen is single bonded to another atom, then you can expect that it's going to be 6 minus 7, which is negative 1. So each of these oxygens on the left and the right will have a formal charge of negative 1. Overall, if we add all of the formal charges together, so 0 for the oxygen with the double bond, plus 1 for the central nitrogen, and minus 1 for each of the oxygens, then we'll get a net formal charge of negative 1. Because that formal charge is equal to the charge of the ion, the polyatomic ion as a whole, that's perfect. So that means that this nitrate with the minus charge will be stable with a formal charge overall of negative 1. We can expect to see the nitrate ion to be in these 3 states essentially simultaneously. So it's going to be in a hybridized version of these 3 states where the pi electrons are shared between the 3 oxygens. Notice how the positive charge is located outside of the nitrogen in all 3 of these. Whenever we have a situation where the formal charge needs to be negative or positive on a given atom, the more electronegative atom, which is going to be oxygen in this case, should be the one that carries the negative formal charge. And the less electronegative atom, even though nitrogen is fairly high in electronegativity, because it's lower in electronegativity than oxygen, it should be the one to carry the positive charge. That again is a concept that you will see with resonance when we talk about organic chem and biochemical concepts. Altogether, to wrap things up, valence electrons are the building blocks of bonding, and Lewis structures show us where they go. I highly recommend getting comfortable doing Lewis structures and noticing the typical behaviors of the atoms together and individually. The keys are to count your valence electrons, be familiar with what valence electrons are removed from each group, be familiar with the octet rule and the exceptions to the octet rule, such as an incomplete or expanded octet. Check your formal charges, and make sure that you know the different resonance forms when necessary. Keep in mind that the more electronegative species is the one that should have the negative charge. The less electronegative atoms are happier with the positive formal charge. The net formal charge needs to equal the net charge of that molecule. If the molecule is a polyatomic ion and has a net negative charge of 1, then the net formal charge needs to equal -1. If the molecule is not charged whatsoever and is supposed to be neutral or at the ground state, then your net formal charge should equal 0. You'll be using this information for VSEPR theory, polarity, different types of intramolecular bonding, hybridization, intermolecular forces, and so on. Very fundamental concept to general chemistry. I hope that this was helpful. Thank you for watching and have a good one.